Okay, let's get started again. Before we move on and get back to our example, I'm just taking a look at the NTHU calendar to see what's going on with classes. All right, where are we? We are today in March 29, right? Yes. Now I'm a little confused because everyone tells me, and yes, Friday is a national holiday, but according to NTHU calendar, it's not a class holiday. Like, it still lists Friday as not a holiday. So anyway, this class is not on Friday, so it's not a big deal, but I have another class on Friday. So for those of you with Friday classes, do confirm whether Friday is a holiday or not, okay? Maybe this is a mistake on the NTHU calendar, so we have to find out about that. Arturo, can you hear me in the back? Yes? Okay, great. One more thing. I've got really, really bad news for you all. So please don't be angry. Next Monday, there's no class. Oh, yeah, thank you. It's okay, it's okay. You'll survive. All right. And I've got even worse news for you. That means that the homework assignment I give this week will not be due next Monday, but the Monday after. Oh, poor people. Then I've got some good news for you, okay? The good news is that your peer review is still due this coming Monday. Yay! All right. So let me just say that again, very careful, and remind me to send out an announcement about this, okay? So just to say it again, the homework for this week is not due next Monday, it's due 2 Mondays. It's due the Monday after next, okay? No. It's due April 12th, yes. Okay, so the homework I give today or tomorrow, whenever, I may not get the homework out till Tuesday or Wednesday. Don't be angry at me because it's not due on Monday, it's due on the 12th, okay? And actually, I kind of like it when students work on the homework, not just exactly the midnight before it's due, but a little bit closer to the class date, because then it's really fresh in your memory when you come to class, okay? But it is due on the 12th. However, your peer reviews for homework number 5 will be due on the 5th, or actually, yeah, by the 5th, okay? But I hope we can get it done by the end of this week so that my TAs can start compiling the grades sooner rather than later, okay? Okay, so that's the 2 announcements I want to make about date and time. All right. Okay, let's go back to our story here. Halim, everything good? Okay. So we're looking at this example, right? And we're having this weird situation where we have a mean of 20 and a hypothesized value of 6. It should be very simple to just discredit this hypothesis, right? However, our standard distribution is 77, so our standard error is also going to be quite big. Does t-test t.test not tell us the standard error? Well, the standard error is quite big. All right. What is the standard error? Did I compute it? Let me see if I did. Oh, well, I didn't, but let me do it here. So it's going to be the mean, the standard deviation, and the standard error is going to be, what is it going to be? What's that? How do you compute the standard error? Mean minus hypothesized mean? No, that's you getting to the t-statistic, I think. Okay, what's in the numerator? The mean. The mean of my sample, or the mean or the hypothesized mean? That's okay. Very okay. So we're gonna look at Alentis mean. Is that right? Yeah? Mehtab, are you with me? You think so? Divided by Atlantis SD. Yeah? Guild, are you on board? What is the formula for standard error? It's the standard deviation divided by the square root of the length. Right, yeah. All right, glad to see some people are skeptical. All right. It's the standard deviation, which is Atlantis SD divided by square root of, oh yeah, I haven't calculated the length, have I? No. Length, so my data set is called Atlantis, right? We just had this conversation with another student during the break. What is the length of Atlantis going to be? 103, right? So if you look at Atlantis, it's this size. Now you have to be careful about this though. The data I loaded was called load times, right? That's the data I literally loaded from the CSV file, right? You have to be careful about checking the length of your variables because what is the length of this going to be? Let me take a look at load times again. Well, here's called page loads for some reason, but what is the length of this going to be? You might be tempted to say it's going to be 104. Let's take a look. It's 2. When you've loaded a data frame and it has multiple columns, length tells you the number of columns. Okay, so be careful about that. If I wanted to, so I could use Atlantis because in my code, Atlantis is really the column that I'm interested in. So now the length will be 105 or whatever it is. Okay. If I wanted to get the number of rows from load times, how would I do it? Clearly it's not length. What should I use? Anybody? There's a function called nrow, and that gives you the length of the number of rows of your data. Okay. All right. So let's go back to what I was doing. So Atlantis SE is the standard deviation divided by the square root of the length of Atlantis. Okay. All right. Okay. And I'm going to use because I'm just doing it at Atlantis right now. I'm not going to use nrow because you may notice the two data sets have different lengths. Okay. And you will see that here. If you scroll to the bottom, you will see that Atlantis has a few more data points than HostMonster. All right. So I'm going to use the length of Atlantis. And the standard error here is 7.65. So that kind of helps explain why my mean of my sample is 20, and yet I'm unable to discredit a hypothesis of 6 even easily. The standard error is quite big. All right. All right. So where was I? So here I did a t-test on the Atlantis data sets, and apparently I cannot reject the claim. Too bad. All right. Okay. So what's going on? When I visualize this, I notice that actually we have a whole bunch of outliers, and this might be causing a problem. What problem might it be causing? I don't know yet. Let's take a look. So let's go to the bootstrap. Let's try to actually bootstrap, and let's try to actually simulate these two distributions, the null and the alternative, to see what's going on. All right. So back to the Atlantis data sets. So we did it the traditional way. We did the visualization. Let's do the bootstrap. All right. So once again, I'm going to do the alternative as the mean of each resample minus the hypothesized mean, and the null value of t as the mean of the resample minus the mean of the original sample itself. what the world would have looked like if our hypothesis was exactly correct. All right. So let's set up. We've set up that function, the hypothesis, and we're going to now replicate. Okay. Okay, let's take a look. Bootstrapping done. Get the alternative. Plot it out. All right. You notice my alternative distribution, even though it looks kind of normalish, the mean of those values is actually a little bit to the left of the peak of the distribution. Okay. Let's look at the null values. All right. And what you will notice now is when I look at the my t value right here, okay, the mean of the t values at least, it's outside the 95% confidence interval of the null distribution. All right. What's going on with our null distribution? Our null distribution is not looking very normal, is it? It's actually skewed considerably. There's values on the left tail that makes it fatter, considerably fatter, and the right tail comes down quite nicely, but the left tail is quite a bit fatter, and there's values that keep going on the end. This is a result of, well, both the fact that we have outliers and our sample size is not all that big. Okay? So this is an example of where the classical approach of hypothesis testing might be problematic, because the assumptions we usually make is that the null distribution in classical hypothesis testing is that the null distribution is going to be nearly normal. It's going to be a t distribution that's quite a central t distribution that's nearly normal, and which means it's going to be very symmetric. All right, but we can see in our simulation that's not the way it's coming out. All right, this would be one example of where we might actually prefer to bootstrap rather than to use classical hypothesis testing. All right, unless someone tells you, just throw the outliers away. All right, but if you cannot throw the outliers away, and in this case I don't want to, because clearly there's customers who are waiting nearly 500 seconds for a response, it would be very rude to dismiss their slow loading times. All right, but an example of where bootstrapping is extremely powerful. All right. Now, if everything was great and the null distribution was normal and our data looked very clean, we probably don't even need to bootstrap. But this is an example of where we probably would need to bootstrap. Okay. The other place where we typically do need to bootstrap, almost always, is when we're not doing a hypothesis about the mean, but we're doing a hypothesis about some other statistic, like the median, where we do not necessarily know its sampling distribution. All right? Great. So altogether, you can use the alternative distribution, you can use the null distribution. However, be sure to not assume that your bootstrap distributions are symmetric and normally distributed. All right? Especially if your data is funny. If your data is not funny, then maybe you don't even need to do bootstrap. But if you're bootstrapping, use quantiles to figure out the 95% or 99% confidence interval as you see fit. Okay? All right, cool. So this is this kind of concludes more or less my comments for hypothesis testing and the bootstrap, and why we want to use the bootstrap during hypothesis testing, and the precautions we have to take. So the main things we've mentioned over the past couple of weeks is we want to bootstrap not just the mean or the descriptive statistic of interest. We want to bootstrap not just the difference from the hypothesis. The most accurate bootstrap will be when you bootstrap the statistic in question itself. In the case of means and the hypothesis of means, that's the t-statistic. All right. And the second thing is, having bootstrap, don't assume your bootstrap distributions are normally distributed. We know that the alternative distribution is not normally distributed, it's actually skewed. And what you can see is if the data is funny, then even the null distribution can be not normal. All right, so use quantiles to figure out your confidence intervals. All right, and I might even encourage you, look at both distributions, because remember, your hypothesis is a story of two competing distributions. So why not look at both of them? All right, great. So that's the purpose of this example of Alentis versus host monster. I might have another question about this on the homework. I don't know yet. We'll see. All right? All right. Any questions on the example I just did? Yes?
So here is another appearance of the contradiction between the classical
Yeah.
statistic and the bootstrap.
Right.
So
Which-
how do we tell our clients to say that your
Right.
hypothesis is wrong or
Yes. So I will once again have to beg you to wait 1 week. There might be something on the homework which will help us justify. So in this case, first of all, I would argue we have to use the bootstrap here for two reasons. One, it's clearly different than the classical results. If it was very similar and the data looks quite okay, then I would probably prefer the classical approach. Since we know that the data has this very weird distribution, and it's affecting you can see that it's affecting the null distribution, I would not trust the classical statistical result here. I would trust the bootstrap. However, we now have to go to the client and tell them we are not doing classical hypothesis testing, we're doing a bootstrap, right? Assuming they know the difference. If they don't know the difference, you're in luck. If they don't know the difference, you have to make a justification. And the justification would be the shape of this null distribution, that it is not normal. And therefore, we cannot use classical statistics, which depends on it being a symmetric, nearly normal distribution. However, they may get back to you and say, what are you talking about? Looks normal to me. And now you have to get into a debate of what is normal, what is not normal. So we will maybe try to approach that debate in the coming homework or the coming week in one of those two situations. Okay, cool. All right, great question. All right, and just a little reminder, we have seen a very simple use of a t-statistic to compare the mean of a sample against a hypothesized mean. You also probably remember that there's other types of hypothesis tests just about the mean. For example, there's hypotheses tests where you're comparing the mean of two samples, not the mean of a sample versus a hypothesized mean. There's situations where you're comparing the mean of one sample against the mean of another sample to ask if these two means are similar. In those cases, your t-statistic is going to look quite a bit different. All right, this is the t-statistic when you are comparing two samples, but you can, for some reason, assume that the population that these two samples come from, the two populations these samples come from, have nearly identical dispersion, standard deviation. In which case you have this t-statistic with this degrees of freedom, all right? Just that the standard error calculation is going to be, you're going to be pooling your standard deviations here. This is called a pooled standard deviation. So there's going to, the standard error is going to look, the formula will be different. What if the two samples are coming from populations with dissimilar dispersions, where you cannot assume that their standard deviation of the population is going to be the same? In that case, assuming if your sample size is big enough, you can use the standard deviation of the two samples like this, S1, S2. If for any reason you are using very small samples, then your degrees of freedom looks like a hot mess. Okay, it looks something like this. What should you do? Well, you can do bootstrap if you need to bootstrap. Maybe you don't need to bootstrap. Maybe the data looks perfectly okay. There's not any outliers. It's just the mean. You can do classical statistics, no problem. If you need to bootstrap for some reason, maybe the data looks very weird and there's all kinds of outliers and it's you have some reason to suspect that the null distribution will not be very symmetric or normally distributed, then go ahead and bootstrap by all means. However, use the correct t-statistic. And one way to get the correct t-statistic is actually to use the t-test function and to tell it your assumptions. All right? This is the t-test function that we saw before, but in this case, instead of giving it a sample and a hypothesized mean, we're giving it two samples. Okay, we're giving it two samples. We're telling it the alternative distribution, and we're telling it the assumption of whether we can assume the variances or the standard deviations of the two populations these samples come from are equal or not. All right? And the t-test function will use the right t-statistic and the right formula for degrees of freedom. It'll pool things if it has to, etc. All right? And here's an example of where there was a third example of we're comparing means of samples that are dependent on each other, meaning question. On this side? This side? N1, oh, excuse me, yeah, I'm sorry, there's a typo here. This one should be N1 minus 1, yeah. And again, I'm going to assume you're not typing this by hand, you're just using the t-test function though. Okay, thank you. TAs, one more job for you. My TAs are like, why don't you just do this right the first time? I don't know. I don't know. What's the fun in that? Okay, thank you for catching that. So just use the t-test function. So this is an example. So this third example is where your samples are actually related to each other. And an example of that where samples will be related to each other is this. Let's say you are doing some athletic training. You're training some athletes. And you're trying to find their performance before and after a certain training regimen. Well, the data from before and after will be related because this is the performance of an athlete before training and this is the performance after training. However, it's the same athlete. So actually these two numbers are related by the fact that it's the same person you're looking at. Similarly, the second number here is going to be related to the second number here because it's the same athlete. One of the reasons they're so similar is not just because of the training, but because it's the same person. So here we do a paired test. So once again, you can do a t-test function and just tell it these two samples are paired. Okay. So use the t-test function built into R depending on the scenario of what you're testing. Okay. And it may not be t-test. It could be another type of test. It could be an f-test, chi-square test. It could be something altogether different. All right. But you can still bootstrap, but bootstrap for the relevant statistic. Okay. All right. Cool. The last thing I want to cover today is going to be about a different type of test, just to show you one other type of test other than the t-test. And it's going to be a test, again, that you're all very familiar with, hopefully. And that's going to be the f-test or the f-statistic. And one place where we use the f-test is when we are comparing variances. All right? So, all right, so in this case, let's imagine that we go back to Alentis and say, we reject your hypothesis, we did this test, and yeah, you guys are in trouble. All right? So we're going back to the Alentis host monster example. Okay? So, and let's say Alentis is furious at us. They're irked, they're pissed off at us. Okay? And they say, well, this is not fair what you've done. Okay? First of all, the outliers are exceptional events. They were not in our control. Yes, it affected us on those days and not host monster, but that's another very complicated thing you wouldn't understand. But it's not fair for you to use the outliers. So first of all, they ask you, please remove the outliers. Okay? And then they tell us, look, listen, our systems are totally different. You shouldn't be comparing the mean. You should be actually comparing the variance, the dispersion of our loading times. This is a very imaginary problem, okay? So they come back to you and say, don't test for the mean. What our claim is actually that the standard deviation or the dispersion of loading times should be roughly the same for whichever hosting company you're using. So we would like you to do the hypothesis test on the variance, not on the mean. All right? So two things. One, remove the outliers. Two, do the hypothesis testing on the variance. Woof. All right, Alentis, let's do this. So first of all, we want to identify the outliers and remove them. Okay, so let's do this. Do I have the code here, or do I have to do it from scratch? I think it's right here. All right. So I think I don't need those for the most part. Do I need them? Do I need them? Do I need them? No, I don't think I need them. Let's give it a shot. Okay. So I'm going to wipe out my plots and move to this new problem. Okay. So I'm going to load the load times. This is Alentis. This time I'm loading host monster. Notice that host monster is going to have a whole bunch of NA values at the end because we don't have data corresponding to Alentis for those instances. Okay. And I think in your swirl tutorial, did you see this na.omit function in your tutorials? If only, yeah, one person is nodding, so that means you all saw it. Whether you remember it is a different issue. I'm only asking if you saw it. Clearly you saw it, okay? So I'm going to ask to omit these NA values for my host monster data sets. All right, great. So let's do little box plots. Let's visualize the data with the outlier. Oh, okay, we have to remove outliers, right? So this is our Alentis data set. It has a whole bunch of outliers. And what are the outliers? If you store the result of the box plot in a variable, then that variable has an out attribute that tells you these are the outlier values. Okay. Now, there might be a better way of doing this, and I'll leave it to students to offer better ways of doing this, maybe on your homework assignment, I don't know where. This is how I'm removing the outliers. It's a little convoluted, so bear with me. There must be better ways of doing this. Perhaps you have to load some new libraries to do it. But let me show you my brute force dirty way of doing it, okay? First of all, I know that these are the outlier values, right? I can ask which of Alentis's values is equal to any of these outlier values using this operator, which is in with percentage signs around it. It's literally asking which of these values is in this set. So it's kind of a set comparison for those of you with some familiarity with set theory or with sets, mathematical sets. We're asking which of these values is in the set of values of these outliers. And anybody know what the answer is going to look like? Anybody want to guess what the answer will look like? Like, what will it be? Numbers? Strings? What's that? Boolean? Or what we call in our logical values, right? Yes, indeed. It'll just be true and false values. It'll tell us where true is this value was an outlier. This value, these true values are indeed in this outlier set. Okay? All right. So then, now that I know which ones are outliers and which ones are not outliers, I am interested in the ones that are not outliers. So that same expression wrapped with a not symbol. Did you cover logical values in your swirl tutorials? Yes. Great. So which of these are not outliers? So that just makes it the opposite. All right. The trues become falses, the falses become trues. Now everything that is true is not an outlier. Fantastic. And now I'm going to ask, please give me all the values in Alentis where they are not outliers. All right. And this should give me all the values which And as you can see, all the huge extraordinary values have disappeared. Right. Give me a second. Just one moment. Did you notice where I put my earphones? Just a second. I realize I'm not wearing my AirPods. That's going to make the recording quality a little bit worse. So let me find it. All right. Okay. For those people listening in from home, I apologize if the sound quality has not been good till this far. Okay. Transparency. All right. Cool. So this. So do you understand what I'm trying to do here? Okay. Now I agree, if you are thinking it, that this looks really ugly, or maybe you think it looks really elegant. Quiz time. How many of you think this code looks super elegant and you like the way it looks? I'll give you extra credit. No, I'm kidding. How many of you think it looks a little ugly and very hard to read? TAs write their names down right away. Okay. Let's see who these people are. Okay. Well, how could I make it look a little bit different, a little bit better? I don't know, but let's try this. I know that this is a logical statement, right? So let me give it a name. This is, I'm going to call it is outlier. How about that? It is an outlier or it is not. Okay. And I can already make this quite a bit better by writing this as not is outlier. That's already a little. Do you think this is a little bit more readable? Hands? Yes? One person, two people? A little bit more readable already? Not is outlier. Or I could just go a step further and say is not outlier. All right? Not is outlier. Right? And now here I can just write is not outlier. Or maybe I can just say not outlier. How about that? Don't have to write everything in English perfectly. Does that work? And does that give me the same results pretty much? Yeah, it does, right? So this is just an example of how, yes, sometimes in R things can be really ugly, but you can also take a little bit of effort to give things friendly names, store them in variables, break it up a little bit, and try to make your code a little bit more readable. So I think now, so here's the thing. This is far more readable. I think anybody will know what I'm trying to do here. I'm looking for data values of Atlantis that are not outliers, right? Now, what is not outlier? Well, if you really want to know that, you have to go read this. Then what is outlier? Then you have to go read this. So ultimately, the ugly code is still here. It's just that I've hidden it a little bit, okay? Is there a value in hiding ugly code? Possibly, because maybe my code is at least people know my intent now. People know my intention, what I'm trying to do with this code. All right. It's possible that it may not be that have figuring out how it works forces you to go back to the ugliness, but I can't help that. Okay, right now. Okay. Um, But still, I think even this ugliness is more readable than what I had up here, because this is simply a set comparison. What values of this data are in this set? That's quite readable. And this is very readable. I'm just looking for things that are not outliers. Literally, not is outlier. And then this becomes very readable at the end. Okay, so I think putting a little bit of effort into making your code readable really pays off. All right, and it's not that difficult. It usually just boils down to coming up with some really friendly variable names, like most of the time. Okay, and breaking down the operation to something simpler. All right, cool. So now let's do a box plot of. So remember the box plot of the full Atlantis data set looked like this, and I can barely see the box. It's there. Okay, let's look at it without the outliers now. Does this give me what I want? Yes, and this even gives me the outliers. So now I still have some outliers. Interesting, right? Removing outliers doesn't mean your new data set has no outliers, because the 1.5 IQR rule simply adjusts to the new IQR. And according to the new IQR, there are still outliers. All right. However, I have got rid of the big outliers, and now the remaining outliers are fairly reasonable in size, I think. Okay. It's debatable whether you want to keep doing this exercise until there's no outliers. But that's not what Alentis asked me to do. They simply said remove the outliers from the data set. I did. Too bad there's new outliers in the new data sets. Okay. All right. So now if I plot the density function of this, it looks a little bit better. There's still, you can still see there's, outliers over here, but it's not like super stretching out forever. Okay. Oh, excuse me. That was the original data set. I'm making a mistake. This was the original. What am I doing here? Hold on. Excuse me. The first is the host monster data set. The second is the Alentis data set without outliers. Okay, and I think these are quite comparable, right? Because I'm not removing host monsters outliers, and I could ask what is the, well, I'm not going to ask, but you can see the outliers of host monster look quite similar now to the outliers of Atlantis. So I think this is a fair comparison. All right, cool. All right. And now we're asked to compare the standard deviations of these two things. All right. So I've got the numbers here. I wish I didn't, because then it'll be a little bit more dramatic. But by and large, these two distributions, even though one is shorter and therefore wider, they look similar in their, they look relatively similar in their range, do they not? The range of Alentis is like 0.4 to 2.12.29 without the outliers. And the range of host monster is, I mean, to me, it's almost identical. It's almost the same range. So I think I could easily argue with Alentis, this is a fair comparison because the data is of a very similar range, 0.73 to 11.77. The two ends of the ranges are off by less than 0.5. That's pretty good, okay? Now remember, Alentis asked me, allegedly, in this example, to compare the variances. The variance of Alentis without the outliers is 7.91. The variance of host monster is 2. That's a big difference. Isn't this interesting? The range and the variance are simply two ways of describing the dispersion of data. And yet, in this case at least, the range makes it look like the dispersion is very similar, but the variance makes it look like they're very different, right? Are they actually very different? We have to do a hypothesis test. Okay. Okay. And how shall we do this hypothesis test? Well, we're going to use the F statistic to do a hypothesis test. And the F statistic is basically where you're comparing two variances. And the way we do it is rather than subtracting one variance from the other variance, we divide one variance by the other variance. Why? Because the division of two variances produces a very well-known distribution, the F distribution. Okay, so the F distribution is defined as one variance divided by the other variance. Notice here I'm using S, that's the standard deviation, so S squared is the variance. Okay, so when you divide one variance by another variance, assuming, and this is a big important thing, that the numerator variance is bigger than the denominator variance. You have to order them correctly, okay? The numerator variance has to be the bigger value, and the denominator variance has to be the smaller value. So where variance 1 is bigger than variance 2, then you have an F statistic which follows an F distribution. Now the F distribution has not 1 but 2 degrees of freedom, all right? In part because you remember your variance formula has a degrees of freedom built into it. We have two variances, they each have their own degrees of freedom. So the F statistic will have 2 degrees of freedom, one called df1 and df2. Okay, and that's simply the sample size of your first sample minus 1 and your second sample minus 1, where sample 1 and sample 2 are again such that variance 1 is bigger than variance 2. Okay, so that's how we pick which one is sample 1 and sample 2. Um, oh, one more assumption. Ouch. An assumption of the F statistic and the F distribution, I should say, is that the populations of these two samples should be actually fairly normal. This is not an assumption we have seen before. With the mean, with the population mean, remember, the sampling mean is normal regardless of what the distribution of the data is. We don't care about the data's distribution when we're doing hypotheses involving the mean statistic. Now we're doing hypothesis involving the standard deviation, the variance. And the F distribution, and we're doing a ratio of the two variances because it has a very well-known distribution. And that well-known distribution is F distribution, but it assumes the populations the data is coming from, of the two samples, is in fact normal. Are these two normal distributions? How many of you say no? These are not normal distributions. How many of you say, yeah, these could be normal distributions? Just me? Okay. They have this nice little bell shape, but then they have this skewing business going on, right? So I take it that's why you're saying it's not normal. Again, we'll ask as maybe part of the homework or maybe next week, how do we really define what is normal and what is not normal? Like just your eyes and my eyes? Well, it does come down to that, but do we have a better tool than just this? Okay, so we'll take a look at that later. Okay, so we have a little problem here. The classical hypothesis testing using the F-test is going to be problematic because the assumption that the two populations have normal distributions is likely not true. Okay. Regardless, let's do the classical hypothesis test here. So the classical hypothesis test, and I believe I've written something wrong here, but anyway, let me just do it my way, which is first of all, I want to know. So this is what, by the way, so this is what F distributions look like. Like the T distribution, the F distribution is not a single distribution; it's a family of distributions, and the distribution of F can look like any of these curves, depending on your degrees of freedom. All right. As the degrees of freedom get bigger, you get closer and closer to this tall distribution of F that you're seeing here, which has a long but narrow tail. As your degrees of freedom are smaller, you get something closer to this shorter distribution with a fatter tail. All right. So F is a family of distributions. You will also notice that if these two, by the way, if these two variants, if the variance of two different samples are the same, what will be my F value? 1, right? Because the ratio is just one variance over the other variance. So if indeed the null hypothesis is correct and the distributions actually have the same variance, the F statistic should have close to a value of 1, right? And so if you look at all these F distributions, you will notice for the most part, they peak very close to a value of 1. This is the null distribution of F. Okay, so whereas the null distribution of T is centered around 0, because we're looking at a difference, which should be 0, here we're looking at a ratio, which should be 1. So they'll be kind of distributed around 1. All right? And I can ask, given an F distribution, and this is a perfect F distribution, but given a perfect F distribution, what should be the cutoff value of F for, let's say, 95% confidence? And it tells me the cutoff value is actually close to 1.4. So values bigger than F values bigger than 1.4, we can possibly reject them. All right. Notice here that we're not doing a two-tailed test. The F test is almost always one-tailed. Why? Because one of the assumptions is you put the big variance on top of the small variance in the bottom. Okay? So your F value can never be smaller than 1 to begin with. all right? So your bigger variance, remember, you write it in such a way that your bigger variance is the numerator, all right? So as a result, your F value will never be smaller than 1. It'll always be a little bit bigger than 1. So we're just asking how much bigger than 1 is too big. And using the QF function, where we give it 2 degrees of freedom, which is the length of each sample minus 1, it tells us the cutoff value for 95% is 1.40. So given our degrees of freedom, F values 95% of the time should fall below 95% if our null hypothesis is correct. And if you want to reject with alpha of 5%, then you're looking for F values bigger than 1.4. All right. So let's give it a shot. I think I've written this actually wrong, but I'm just using, so there's 2 ways to do it. So one is you simply calculate the F value like this. The F value is literally the variance of, why did I write it like this? This should be TAs, this should be Atlantis omit outliers. Sorry about that. My poor TAs have so much work to do. All right. So it should be the variance of one data set divided by the variance of the other data set. Okay. And I get an F value of 3.82. And 3.82 is quite a bit bigger than the cutoff I was given of 1.4. So I can likely reject this hypothesis that these two variances could possibly be equal. All right. This is the classical F test. There is a var.test which tests variances and give you F results. I think I've set it up incorrectly because the 95 confidence interval should be, let me take a look at that later, okay? Bless you. All right. We can also bootstrap this thing. Why would we possibly want to bootstrap it? We have this beautiful F value. It's because of this assumption that the two distributions have to come from normal populations. Clearly none of you are comfortable assuming that these two distributions come from a normal distribution. Nobody raised their hand. So the class, since I cannot make this assumption on democratic grounds, I have to do something else, all right? And in my case, what I'm going to do is I'm going to just bootstrap it, all right? So let's do that. All right, so we did the traditional way. I didn't really run it, but I showed it to you on screen. Let me actually try to run the actual bootstrapped version of it. Okay, so here is my bootstrapping function, and let's take a look at this function. I am once again resampling, but notice this time I have 2 samples. I'm calling them larger SD and smaller SD, meaning the sample with the larger variance or standard deviation and the sample with the smaller standard deviation or variance, okay? And I'm expecting that they'll be passed in appropriately. So, excuse me, I'm now resampling from each of these 2 samples. I'm resampling from the sample with the larger dispersion, and I'm resampling from the sample with the smaller dispersion. So I've got 2 resamples in each iteration of this bootstrap. I've got resample of larger SD and resample of smaller SD. Okay, these are just 2 resample data sets. Okay, my alternative distribution of F should be centered around this computation. The variance of the larger of the sample with the larger variance divided by the variance of the sample with the smaller variance. All right. What about the null? Well, in this case, and there's 2 ways to do it, as you can imagine, but in this case, I'm looking at the null like this. I'm taking the variance of the larger resampled sample divided by the variance of the original larger sample. Okay. Once again, I'm trying to simulate a situation where my hypothesis would be correct. all right? And my hypothesis would be correct if my second sample happened to look exactly the same as my first sample. So therefore, I'm resampling from the first and comparing it to the original of the first. All right, and this gives me an alt and a null value of f. So I'm gonna set the seed. I told you this is a bad habit of mine. Don't do this. Don't always set the seed to be 42, 43, 1, 2, 3. Just try to pick a crazy seed every single time. You can either just mush your number pad, or as I showed you last week, you can use the random function just to get or the sample or the random function just to get a very, very bizarre seed, okay? But it's my bad habit I'm asking you not to do. So let's replicate this, and I'm doing this 10,000 times, by the way, now. Ooh, finished. That was quick. Cool. So I'm doing 10,000 resamples here. And the F statistics that come back will have 2 rows and 10,000 columns. The 2 rows will be the alt values and the null values. Okay. I can look at the null values and directly ask, where is the 95% quantile for the null values? And you notice it's at 1.32. In the classical way, when I asked the QF function that for a beautiful F distribution, what should the 95% cutoff be? It was 1.40, 1.41. Okay. Whereas now I'm getting 1.32. Interesting. All right. I'm also going to show you the median value, by the way. The median value is quite a big bit this is the median of the alts. Oh yeah, so I'm showing you the 50% of the alts, okay? Let me visualize this out. So this is that's the distribution of the alt distributions, and that's the distribution of the null F values. Do you see how different they look, right? The blue is the distribution of the alternative distribution of F. That's the F statistic literally bootstrapped. And then when I simulate the null distribution, it's got this shape to it, okay? It looks, I don't have an example of it. Okay, all right, all right. So these are the 2 distributions, the alternative and the null, all right? And I'm going to draw the 95% confidence interval for the null in red, okay? One-tailed because the F value cannot be smaller than 1, all right? And then I'm going to draw the F value, the actual F value that I get from my computation, right? This is not the F value from the alternative distribution. I believe this is the F value from originally computing the variance of Alentis versus host monster. So the actual F value, all right? So my actual F value looks like this. It's distributed like this blue distribution. The null is distributed like this, and the 95% cutoff of the null is here, all right? So my F value is far, far away from the 95% confidence interval of the null value of F. It seems to be a ridiculously high value. So we can probably reject our null hypothesis and tell Alentis, no, your variances are not at all similar. Okay? Question? Why the formula? Oh, you mean in my code? Or you're asking in the code. So there's 2 ways that I could have done this, and the way that I chose to do it is, so for the null value, I am basically trying to simulate a world in which the 2 variances are the same, right? Because the F statistic is comparing 2 variances, right? And we're asking, are they different? And what I'm trying to do with the null value here is trying to simulate a world in which the two variances are the same. So I'm keeping the larger, I'm just using the larger sample here. I could use a smaller one. Maybe I'll discuss that the next time we come to class. But for now, I'm picking the larger, the sample with the larger variance, and the numerator will be the same as my typical F computation, right? However, in the denominator, I want to compare this resample against a sample that should have, on average, the same variance. And the sample around which these resampled larger values should be centered is the original sample with the larger variance. You don't look convinced. All right. I'm just trying to create a situation where these variances will on average be equal to this variance. That is the null hypothesis, right? And these variances, on average, what will they be? On average, they will be this larger sample from which these are being resampled. Okay? So since I'm resampling from this, I know on average this value, the variance of this resample should be the variance of this original sample. That's why I'm setting up this null hypothesis this way. If it's still not helping, maybe ask me one more time on our discussion board, and I'll try to see if I can help. Okay? All right. So this is how I'm doing the alternative and the null in this case. Okay. I'm simply trying to create a scenario where the null hypothesis will be true, where it'll be close to 1 every single time, and on average it should be 1. Okay. And hopefully you kind of see, well, it's a little hard to see, but on average these values should be about 1. Okay. The null should be around 1. That's what makes it the null. Yeah. Yes, so there's two ways to do it. One is you could look at the confidence interval of the alternative and see if the 95 limit of the null is in that distribution or not. That's one way you could do it, right? I think that's what you're saying. You could look at the confidence interval of the alternative and see if this cutoff value is in that 95% confidence of the alternative. The other way to do it is to look at the confidence interval of the null and ask if the original F statistic is in that confidence interval or not. It's the same thing, one or the other. In classical hypothesis testing, we're focusing on the null distribution, so that's why I'm doing it this way. All right, but you could also do it the other way, looking at the alternative distribution. Yes. All right. So this is just a quick demonstration, and I've tried to visualize it here, that this is a quick, now I want to mention a couple of things here with this distribution, all right? With these two distributions. First, if I was to only look at the distribution of the alternative distribution, it actually looks like this. It looks quite nice. It only looks really short and squished when I plot it relative to the null distribution. The null distribution is so much taller that my alternative looks so short. But you notice the peak of my alternative distribution is around 0. Let's say 25, right? So, and that's what it originally looks like, okay? So this does have an F shape. It just looks really squishy compared to it looks really short compared to the null distribution. That's one thing I want to point out, okay? There's one more thing I want to point out that nobody has asked me yet. I'm so disappointed. Okay, no. Remember, I said we are doing the alternative value of F following the classical F statistic. We're putting the variance of the sample with the larger variance in the numerator and the variance of the sample with the smaller variance in the denominator, right? So this ratio should always be bigger than 1. Is that ratio always bigger than 1? If you take a peek down here, this distribution is still coming down this way, and it looks like, could it be? Let's take a look. I'm not even sure, but let's look at f alts. This should be all the alternative values of f, right? And I can ask f alts less than or 1. Okay, this should give me true and falses. And how can I get how many are true and how many are false? Have any idea? Yeah, the sum might actually work. It can actually treat 1 as true as 1 and 0 as false as 0. And this tells me that actually in 3 cases out of these 10,000 bootstraps, I had f values smaller than 1. Dong, dong, dong. What's going on? This is just the nature of the bootstrap, okay? Because we are resampling, sometimes when we are resampling from the sample with the bigger variance, we're just by luck or lack of luck missing the big values, and we're getting a sample with very small variance. We're missing the extremes for some reason, and we're getting a sample with a small variance. Or possibly, yeah, I guess that's what's happening, right? So sometimes the bootstrap is actually returning to me F statistics that are smaller than 1. Is that a problem? Does that mean the bootstrap doesn't work? If we look at my handout, and this is like the family of F values, right? You will notice these are null values of F. For null values of F, even though we are typically putting the bigger in the numerator and the smaller in the denominator, even the classical F distribution does assume that a big section of null values of F will be smaller than 1. Okay? So the F distribution does assume that in this universe, you can get F values that are smaller than 1. We try to arrange it so we don't get it, but the F distribution does take into account that you can have values smaller than 1. So don't be surprised that in our bootstrap, we pick up the same thing. We pick up some values down here, which have alternative values, which have values smaller than 1. Okay? So this is the bootstrap with a completely different test, not the test of means, not a t-test, but with an f-test. So I'm showing it to you just to kind of show you, you can do a bootstrap for any statistic, for any test, but you kind of have to still understand the basic statistics really well to ensure that you're setting it up correctly. All right. And in this case, I'm using an F statistic instead of the T statistic. I don't want to belabor this point because we'll talk more about the F test and the bootstrapping it next week not next week, 2 weeks later in class. All right. Why are people smiling? You look happy. No, no. All right. And that's really all I want to say about bootstrapping the bootstrapping tests, the hypothesis test. You've seen it done on t-tests. You've now seen it done on f-tests as well. All right. Okay, great. The last thing I want to do before we retire for today is just talk a little bit about your homework reports, like what you're submitting and what it looks like, what it could look like. So I want to, if I can, I want to just quickly show you some examples of assignments that got 4.5 or 5 points the last couple of weeks. Okay, I don't know about last week because those peer reviews are due today. So we haven't computed the values for that quite yet. But I'll show you from week 2 and week 3. All right, like some of the week 2 and the week 3 homeworks. I'll show you some of those results, some of those assignments. Now, the week 2, we just picked it up by hand, like the TAs and I looked for pleasing looking reports. Week 3, the homework number 3, I'll show you some examples that was actually peer reviewed as 4.5 or 5. Okay. I've tried to redact or censor the name of the student doing the assignments, but you might recognize your assignment. So this is from week 2. This is one of the homework assignments from week 2 that I think the TAs gave maybe a 5 points to. What did my TAs like about this? I don't know. TAs, what did you like about this? TAs? They don't remember. Did you just flip a coin? Did you flip it or yeah? Did you flip a coin? Well, you flip 5 coins. It's a binomial distribution. Okay, got it. Well, I'll tell you, I agreed with them on these ones, so I'm showing you these. What did I like about it? Well, I liked a couple of things about it. I mean, you can see the code easily, and you can see the result easily, right? And I like that they put the result in a different color. I assume it's the color they got from our studio or whatever, but you can see the result quite easily in each of these things, okay? And I also like that, they very clearly show me this is the question I am asking, and they left a comment in this case about what they're trying to do with their code. In case this is not how you did it, you can still see what they were trying to do, all right? So I really appreciated that, and the answers are visible. I would suggest though, the answer, try not to use an orange color, because on some projectors or photocopies or black and white printouts, orange does not print out very clearly. I mean, orange against a white background is not very distinct. Okay, so you could pick an even or make it bold at least. You can make it a little bit. So, but just to give you a sense that I found this a very pleasing looking assignment. I can clearly see my question. I can clearly see their code. And in case I don't understand their code, they even left me a helpful little comment of what they're trying to do. All right. And then I can clearly see the output value very nicely. All right. So this was an example. And then, yeah, with the histograms, once again, they've showed it fairly well. All right. Okay. The code for the histograms is all up here, and they show me the results down here. So I thought this was very pleasing. I also liked that the box plot has a little alpha transparency on it, so I can see right through it. Or maybe they just did it the other way around. So either ways, I can see it very clearly. So this was an example of homework number 2 that I thought was done rather well. Let's see this one. This is another example. I'm going to close this one. Okay. So let's see this. This is another example. I've just redacted the student's name. It looks really nicely formatted. Some of you may not recognize what the hell this stuff is all about. Don't worry quite yet. Um, and but here the fonts, I really like it. Is the questions are nice and dark. They have written their own assumption in plain English, not as a comment, in plain English, right? And the code is in a, can you see it here? Yeah, the code is always in a nice gray background, and the answer is apparently in a white background, so I can clearly distinguish the code from the output. Okay, so that looks quite nice. I love this font as well. All right, so quite easy to read and see what they're trying to do. All right. I cannot assure you that this I didn't like. I did not need to see all this data, but that's fine. I didn't mention if I wanted to see it or not. All right. Anyway, I just think they've done a really good job at this part is quite as expected. Okay. So just another example of fairly pleasing results. All right. Um, that was my TAs, and I agreed with my TAs on week number 2 because I didn't say anything on week 2, and you'd never seen a previous assignment before, so you were all doing it kind of for the first time, just using your own intuition. So we were a little generous giving away 5s, you guys. All right. Let's look at last week. There was week number 3. There were a few 5s last in the week number 3, but actually more 4.5s. I don't hardly anybody got like 2 peer reviewers agreeing on a 5. But let me see if I can find some examples. All right, so here's, let me just, can I zoom? Okay, so here's an example. This might be the same person as week 2, I don't know. So this person got either a 4.5 or a 5. I'm guessing most of these got 4.5s. So one person said 5, one person said 4. So I really appreciate it. Again, as you can see, the question, I will say I don't think the student had to write this much. They could have written a briefer statement because I was asking for a brief statement, not the copy and paste my whole question. But the code is very pleasing to look at. It's got some colors. I can distinguish the comments from the code. All right. The visualizations are shown tastefully, so on and so forth. They've used a couple of different colors to show like, means and this and that. So I think they've done quite a nice job. I can clearly distinguish things. They've also gone the extra step of writing the equations quite nicely. All right. And they may be using, for whatever formula they're using, they've kind of written it out really nicely as well. So I found this quite pleasing to read as well, right? They've even gone the extent of writing formulas in proper mathematical notation. So this got a fairly good grade, as you can perhaps imagine. Some more examples. Oops, this one has the student ID on it. Oops, sorry. and But this one uses a different approach to distinguishing code and results, but they've just put a little box around it, and then they've actually written in plain English what the result is going to be. All right. So that it's here as well, but they've also kind of extracted it from the code and written it here. So whoever the two people reviewing this, at least one of them felt this greatly helped them understand what they're seeing. And they even wrote like, see the plot. This is the thick line. This is the thin line. Okay. So you may not feel that this is the prettiest thing, but the point here is not to be pretty, is to make it really easy for everyone to understand it very clearly so that the important details get picked out really nicely. So the peer review and the TAs kind of agreed that this was rather well done in a very different way than other well done assignments. Okay, the way they put a box around it rather than shading it, both works. Okay, but I really again appreciate that they say the result is this, and they really get my attention on what is the result. I don't have to go hunting through this to say, okay, what is the result now? What should I be looking at? Yes, the results are in here, but they've also written the results out really nicely. All right, so just some things that we really liked. I should have really, I should have removed that. Sorry. Too late, but anyway. This is another nice one, and they've used shading and a little bit of a light box around it. Huh, interesting. Okay, and a little bit of color, so the comments and the code are distinguished from each other. This is really nice. I really like the way that's done. All right, and so here are the results, and so on and so forth. Okay. Yeah, and I really like this as well, that they've shown the code here, and they've used a separate box with a different coloring scheme to show the output, to show the results. That again makes it stick out really nicely. It's not like I have to look at the code and look at some comments at the bottom of the code. Okay, so just a very nicely done. Again, you can, even as I'm scrolling through this, you can clearly pick out the questions, the descriptions, the code. Sometimes there's comments for the code, and the outputs are clearly distinguished. And then the result is written again very explicitly. Very nicely done. All right. One more, maybe a couple more. Again, a very similar template to another student we saw. Huh. So some people are using similar templates. Where are they getting these templates from? And again, they wrote their equation differently, but again, they wrote their equation in a very pleasing mathematical notation. How are they writing this mathematically? You might ask yourself this. Like, how are they really writing a cube root here, right? So again, very nicely done, written very clearly, the formulas and everything, right? So maybe unsurprising that the peer reviewers said, hey, this was fantastic. And they gave them at least one of them gave them a 5. So overall it was a 4.5. It got my attention, which I'm very grateful for. Okay. This is also really nicely done. All right. The code is written distinctly from the outputs. I will caution about one thing, however. It is pleasing on the screen. If I had to print this out, I would be swearing because I'm losing a lot of ink because I'm using a black background, okay? So that's just one thing to notice. I would strongly suggest not using a black background because if somebody wants to print it out, you're killing their printer, okay? So try to use a white background as far as possible. Um, and also you'll notice on a projector, dark writing on a white background looks better than light writing on a dark background, depending on how dark is dark and stuff. So play around with the colors, but by and large, it looks like this, okay? So, but anyway, people also felt this looked rather clean and easy to read, at least on the screen. My only concern is what it'll do to my printer and what it looks like on the projector. But these are all things you have to think about when you're preparing reports. You always want to think about what does it look like on screen, what will it look like, and what will it do when I'm trying to print it out, and what will it look like on a projector. And I strongly suggest if you know you're going to be projecting a report, try to go to the room in which you'll be projecting it and project a demo version of your report beforehand. You will often find some colors do or do not work depending on the projector, depending on the transmission format. For example, I find if I'm using just a VGA line to my computer, I lose a lot of yellow colors in projection. I lose a lot of gray colors as well. All right. Maybe in that room, the VGA output is broken. I don't know. So always be concerned about these three forms of presentation: online, in print, on projected on a projector. All right. By online, I mean on screen. Okay. So those were the three examples I want to show you. And I want to mention that a few of those examples, they got their nice output, including the formulas, using a technique. Oops, excuse me. I don't want to show this. I want to go back to my, they're using a formatting technique, which I found many students in the class are getting more and more comfortable with, called R Markdown. How many of you are familiar with R Markdown or have used it on your homework assignments already? All right, that's probably half the class. All right. So for those of you who are not familiar with it, well, first of all, you're in luck. There's a fantastic website which I have linked to here. This R Markdown link will take you to this fantastic website that is a tutorial on how to use R Markdown. At least the big level things. If there are smaller things like formulas and things you don't see it, ask us like, hey, how did you guys do formulas in R Markdown? And we will share with you, okay? But the idea of R Markdown is this. First of all, R Markdown is a subset of a formatting syntax language called Markdown. And Markdown looks like this. Markdown files typically have a .md extension. You can create them in R, in RStudio, I mean. And Markdown, without the R Markdown part, just a Markdown, is an easy way of adding syntax and formatting to text. So for example, Markdown looks like this. This is classic Markdown. It begins with 3 dashes, and oftentimes there's some metadata before another 3 dashes, though you don't have to have this metadata, but you start with 3 dashes usually. The file should start with 3 dashes. Here they're saying the title, they're saying, I would like my output to be optimized for HTML for a website. You could also write output PDF, saying, please optimize this for PDF output, okay? And there's a bibliography file even. So Markdown is basically text. You write your text the normally you would write text. If you want to put things in italic, if you want to put things in a bulleted list, you use this dash to bullet them. If you want them in italics, you use the star, 1 star around the words you want italicized, 2 stars around the word bolded, a back tick around code, and it'll be formatted differently. Links can be formatted like this. You put a square brackets around the words you want to link, and then in parentheses right after that, without a space in the middle, the actual HTTP link. Okay. You can do formulas like this. This is this is a subset of the LaTeX format to do formulas. You can do dollar signs, and your formula goes in the middle. There's a special way of showing what is a super what do you call it? Super. What do you call that? Subtext, supertext. Superscript, yeah, what is superscript? What is subscript? Thank you, sorry. My a little bit fading here, okay? You can, okay, so on and so forth, all right? And you can Google for Markdown to find all kinds of things you can do in Markdown. You can do headers, lists, links, images, block quotes, equations from using LaTeX syntax, tables, footnotes, horizontal lines, bibliography, citations, slide breaks. You can define that these are slides and I want to break italicized, bold, superscript, subscript, strike through, stuff like that. Okay, so that's what Markdown looks like. These are .md files usually. R Markdown is adding the ability to not only add R code to your Markdown, but to even execute the code and put the output of the code back into the document. So in R Markdown, we typically have chunks of code that looks like this, triple backticks. This is telling us that the next line is going to be in the R language. You could do it in the Python language, in any language. It's saying it's going to be in the R language, and it's saying, please run this code, but don't include it in the report. So include equals false. When this is being formatted to HTML format, it will run this code, but it will not output it to the report itself. Okay. Um, and if you do want to output something, again, you tell it, this is R code. I have not said include equals false. So this image will actually get output into the report. Okay. And you can even add a little figure caption to it. So this is what this R Markdown looks like in HTML. This is the title. This is a section header. All right. So the title is defined here. Title, Magma demo. All right. This double £sign tells it this is a level 2 header for Magma colors. And this image line, this code is actually executed, and the result of this image is stuck back in here. All right. So this is R Markdown. With R Markdown, you can create, HTML, PDF, even Word documents or open documents. You can create all kinds of things. All right. Even presentations, even PowerPoint presentations or online slides and other things. All right, other types of templates. So go ahead and play with R Markdown or Markdown if you wish. I'm not requiring it. If you're happy with Word, stick with Word. But if you want to play with this, play with this. I will say a couple of things about this before finishing. One thing, please, for the love of God, finish your assignment before playing with R Markdown, okay? One of the things that can be very frustrating is you're trying to play with the formatting and it's taking like minutes and hours out of your day and you're not getting the assignment done. So first, write the code and get the assignment done. Then you can copy and paste the code into an R Markdown file and do all your formatting and outputting and stuff, okay? Make sure you get the assignment done first. Also, I say this because you can get carried away with what you think is a small little formatting and it'll take like the next half an hour of your life. And if you do that, you'll suddenly forget what you're doing on your assignment. So please do the code, get the code done, and then do the formatting later. That's my advice to you from years and years of working with R Markdown and things like that, okay? So that's one thing I want to mention. The second thing I want to mention is you've seen some fancy examples of R Markdown when I gave you, what did I give you? Some of your readings, perhaps. Um, these readings that I gave you a long time ago were actually created in R Markdown. So you can see the colors look similar to some of the colors that you're seeing in the assignments I gave. I was actually using excuse me here. I was using a template called Tuft Book. This follows the style of a famous, like if you will, the godfather of data visualization, Edward Tufte of Tufte. All right. So he's written the classical book on data visualization, which is a wonderful book, and not just one book, multiple books on data visualization. So if you're ever curious on data visualization, go read his books. Just go find it on Amazon or Google it online, Edward Tufte. All right. And there is a template that you can download. You have to download it that will allow you to write text that follows the style of his books. So when I'm showing you this output, this is the style of his books, where he will basically the right 1/3 of the page is empty, and he just puts visualizations or output of code in the right 1/3 of the page. So he kind of does this style, and he's also got the style of writing like the first sentence or the first part of the first sentence in like small caps, and and then sticking code in here, and then where necessary, you can put it in the middle parts, but where you want, you can also put it on the right margin, which is a very fat right margin, okay? And having a nice big right margin also means people can write their notes here as well, okay? So this is the style of Edward Tufte of some of his books. I was copying it for a couple of the handouts that I wrote for you. So that was one handout. The other handout, I believe, also used the same thing. And in this case, I was putting footnotes in the right margin rather than the bottom of the page, okay? So you can play with Tufte's style as well if you wish, after you have finished coding your assignments. Because one thing, on the other nice thing about Tufte is, you can put like extra comments in the right margin, which is really nice, right? Like comments for my code go in the right margin. I do warn, playing with this Tufte template, it's extremely difficult because, oh my God, things change around so much and small things make a big difference. It took me many hours to get this formatting down correctly. So I don't encourage you to play with this unless you really love this style for some reason. But do play with R Markdown once in a while to get familiar with it. I'm not requiring it, but you can see that maybe at least half of those 4.5 assignments, or maybe more, are using R Markdown to get a very pleasing format. Okay. All right, cool. So this is all I wanted to mention, and that's it for class today. So have yourselves a great week. Have yourselves a great 2 weeks. Hope you, for those of you who observe it, I think tomb sweeping is next week. So see you back in 2 weeks. But remember, your assignment is due in 2 weeks, the Sunday before the next class. So it's going to be due on the 11th, I guess. So the next class is the 12th. But your peer reviews for this week are due in 1 week's time. Do not delay on those, okay? Thank you so much. All right, take care. They updated it? What? Why? What are you saying? I can't. No class. No class. Oh. Thank you. Yes.
I have pressure about when I was showing the median of this. I've told you
Oh.
or showing median.
Why I'm showing the median? Maybe I'll discuss that in the next class. But in particular, I guess I'm showing the median because I'm doing quantiles, right? Like 95% quantile, this quantile, that quantile. So just to be faithful to the quantile worldview, instead of saying the mean, I'm saying the median, which is the 50% point.
Because we're showing quantile, so using median.
Yeah, that's why I'm using median. Yeah. I mean, I could use the mean, but I chose to use the median instead, okay?
Okay.
Yeah.
That is my question.
Okay. To show you the center of that distribution. Because the distribution is skewed, so the mean will be a little bit further away. So the median, I think, is a fair representation, and it follows the quantile logic again.
Should I like time two because it's the two-tailed?
Yeah, a lot of students are asking me this. You can times 2. I am only looking at one tail, so I'm doing the p-value like this.
So you're using a two-tailed test.
I am using the two-tailed test, but the result will be the same because I'm looking at the p-value and I'm just seeing if it is to the right of this threshold. The other way to do it is to multiply it by 2 and say, is it bigger than alpha?
Yeah, I'm doing that way.
Okay, that's fine. I'm doing it this way, which is I don't multiply by 2, I actually compare it to the actual threshold.
And you use the alpha.
Yeah, to get the two, yes, exactly right.
Okay.
Okay?
Understood.
Yeah, thank you.
Thank you.
Yes. Hold on, I should put on a mask if we're talking so close. All right, hold on. Just so that you don't complain later that teacher got me sick. Okay, tell me.
Can we like verify why it was like smaller than 1?
Yeah, what you can do, I mean, verify. Oh, you want to ask why it is?
Yeah.
It's because we're subsampling, right? We're subsampling, and we're taking 2 samples, right? And one sample should have a bigger variance than the second sample. Let me maybe do it a little bit on the board. So one sample, if it was normally distributed, should have a wider distribution than the second sample, right? And we're dividing the variance of this by the variance of this, right? However, and this we are passing this in to our bootstrap function. However, when we are bootstrapping, you know we're just randomly sampling.
Yeah.
It's possible that in one of those random samples, we should be sampling like all through this, right? But it's possible, because it's random, that for some reason in subsampling we did not get many of these, or maybe many of these. And as a result, the resampling of this distribution it turned out to be quite weird, like that. So it's an artifact of resampling, okay? But it's not a bad artifact. We don't want to throw that data out, because if you look at the F distributions itself, even if you go online and search for alternative distribution of F, the pure distribution of F also includes values smaller than 1. Even though you're not, so theoretically it's possible. It's just that because you set up your F statistic in a particular way, you never see F values smaller than 1. But conceptually, it's possible. And the bootstrap actually finds that. So that's a good discovery from the bootstrap, okay?
Another question. Let Linda ask.
Okay.
We are a little bit confused. Here, you say there are 2 ways to
Yeah, for the T distribution or the F distribution, there's 2 ways of doing your test from the bootstrap. One is, so let me draw let me draw here like so this is, let's say, the null distribution of your t-test, okay? And let's say that this is the alternative distribution of the t-test, okay? So this is, actually I should null, okay? And this is the alternative. So the null is going to be centered around 0, right? This alternative will be centered around your t-value, right? So now there's 2 ways of doing that. From the perspective of classical testing, we are interested in the null distribution, and we want to know what is the 95% confidence interval, and is my t-value in the 95% confidence interval. So you could simulate the null distribution, and only the null distribution, and ask is the t-value in there. Alternatively, you can simulate the t distribution, and you're going to get the alternative distribution, and you can ask, is 0 within the 95% confidence interval of the alternative distribution? The results should be just about the same, unless you have some weird borderline case. The results should be just about the same. So there are just 2 different ways of doing it. Okay? So by and large, I see this one used the most, where people distribute the statistic of interest, but they have to keep in mind they're distributing the alternative, they're simulating the alternative distribution. So you just want to see, is a value of t being 0 possible in here? If you are simulating the F distribution, then you want to ask, is the value of 1, like where is the value of 1, something like that. Is that within my distribution? Make sense? So that's why I'm saying you can do it either ways. Simulate the null or simulate the alternative. My suggestion usually is simulate both. It just takes 1 extra line of code. All right, and you can ask all the questions you want. Got it? Okay, thank you.
the last one.
Oh, last one.
Is about Friday.
Friday, okay. I think someone told me the school updated it,
Yeah.
and now there is no class on Friday, right?
Yes.
Okay, no class on Friday. So I should tell the security class about that.
So we'll ask homework due next Friday or this Friday.
Please make it this Friday.
Okay.
Well, let me think about it a day longer and I'll get back to you.
Okay.
I'll think about it a day longer and get back to you.
Okay.
Oh, The alternative distribution skews because this is a characteristic of the t statistic. The numerator of the t statistic, if it's not 0, I don't have actually a good explanation, except to say this is the way the t statistic works, the t distribution works. If it is centered around 0, it will be very close to normal. If it's not centered around 0, that's the alternative distribution, it will be skewed. Okay? Why will it be skewed is a great question. I don't have a fantastic answer, except to say it might have something to do with the way that smaller values are being divided by the standard error. Particularly values smaller than 1, when they get divided, they get shrunk between 0 and 1. Whereas values that are bigger than 1, when they are divided by a number, they don't get shrunk to a small range. They can be still in quite a wide range. Okay? So I think that's the reason why this gets kind of squashed on this side and looks skewed. I think it's because values between 0 and 1, however you divide them, they will just stay within 0 and 1 and just kind of contract. Whereas values here, I mean, they will contract but not into a small range like a 1 unit range. I think that's why it's kind of happening. Alright? Yeah.
Can you explain again why we want to use
For which? Yeah. So we've seen two types of tests so far. We've seen tests about the mean, and today we also saw a test about the variance. Right? Usually, when you're doing a hypothesis test about the mean, you don't need bootstrapping. Usually, because the sampling mean is quite robust to all types of distributions, and it will have a normal distribution. So typically, classical statistics works. The example we saw today in class is a little weird because it has all these outliers, and when you saw that when we simulated the the null distribution, it's not symmetric and normal. All right. So when you have data with a lot of outliers, you cannot assume your null distribution will be symmetrical. In a situation like that, the bootstrap might be better. However, if your data doesn't have outliers, you don't need to bootstrap for hypothesis testing of the mean. Okay? Because if you don't have outliers, typically you don't need to. So, hypothesis testing of the mean, I would only use bootstrap when there's a lot of outliers. That's when I would use bootstrap. Because the null distribution is no longer going to be necessarily symmetrical. Now, with the F test we saw today, the F distribution does have a very strong assumption, well not super strong, but has an assumption that the two samples you are testing, the variance of, the two samples should be kind of normal. Remember, the mean does not have this assumption. With the mean, any distribution, the mean will always have a normal distribution. But in the F test, you cannot assume that. You need to assume, you need to be quite sure that your two samples are coming from a fairly normal distribution. In our case, the example we saw for the F test today, everyone agreed that the two samples don't look normal. So it would be dangerous to use the F test, the classical F test, because the distribution may not look like an F distribution. So there, it's safer to do a bootstrap. So we use bootstrap instead of classical statistics when we have very unusual data, or we cannot meet one of the assumptions of the test field. There's one more place where we want to use bootstrap. That's when we're looking for a statistic for which we don't have a formula, like the median. The median, there's a formula for the sampling distribution of the median. So we have to bootstrap.